Okay, so it is my honor and a great pleasure to be able to participate in this Midrasha meeting celebrating Alex's 60th birthday. I've known Alex for many years, but in recent years we've also been able to collaborate, and I'm fortunate with this. We're able to collaborate on some questions on high-dimensional expansion. This is a relatively new area, and it lies at the intersection of topology, combinatorics, and perhaps algebra. And Alex had been the driving force behind this area for the last 8 or 5 years. And collaborating with Alex is both rewarding and a pleasure. Alex is, on one hand, very focused and very enthusiastic about mathematics. On the other hand, he's quite relaxed, and it's a real pleasure working with him, and he will be featured in this talk throughout this talk. Okay, so let's talk about a high-dimensional expansion. And the plan is as follows. We'll first recall the notions of expansion in graphs, just in one-dimensional complexes. We have this, and then we'll extend these notions to high dimensions and see two instances, independent instances, where these notions came up. One is random complexes, and the other is Gromov's celebrated topological overlap theorem. We'll then see some examples of expansion using symmetry. So we'll talk about Metroid complexes and spherical complexes, and perhaps, time permitting, also some complexes. And finally, we'll see a construction of high-dimensional expanders, two-dimensional expanders, using random Latin squares. And we'll conclude with some comments and open problems. But let's start with the graphical case. So in the graphical case, let's see. We have a graph, and we have a subset of the vertices. This is S, and the S bar is the complement of S. And E of S, S bar, is just the number of edges between S and S bar. Now, the Chigger constant of this graph is defined as follows. We'll minimize over all subsets S, non-empty and not everything. And we look at the quotient ESS complement, so the number of edges, normalized by the smaller of the two sets S and S complement. Okay, so clearly, if the graph is disconnected, then HG will be 0. Just take the two connected components. The E of S, S complement, will be 0. And if the graph is connected, this will be positive, and the larger that this will be, the more connected the graph is. So in a sense, Hg is a measure of the connectedness of the graph. Okay, we have another notion of expansion in graphs, and this is the graphical expansion, or spectral gap. Here we look at the Laplacian matrix of the graph, so it's a V by V matrix that has the degrees on the diagonal and -1 in place UV, where UV is an edge, and 0 otherwise. This is a positive semi-definite matrix, and its eigenvalues are 0, the 0 eigenvalue corresponding to the all 1 eigenvector. And the second eigenvalue is called the spectral gap, and really controls many dynamical graph properties of G, namely the rate of convergence of the random walk on G to a uniform distribution, and so on. Now, there is a close connection between the Chigger constant and the spectral gap. And it has two parts. The first part is due to Alon, Millman, and Tanner. And it says that the the cut of S and S complement has at least size S times S complement over N times the spectral gap. Dividing both sides by S, we find that the Chigger constant is at least the spectral gap over 2. On the other hand, Alon and Dudziuk prove that, at least in the D regular case, H of G, the Chigger constant, is bounded by the square root of 2D times lambda 2 of G. And while the exact dependence doesn't really matter asymptotically, these both theorems says that if the graph is expander with respect to the Chigger constant, it will also have a large spectral gap, and conversely, at least when the degree is fixed. Okay, and now the question is how to extend these notions to high dimensions. So both these notions have natural extensions to high dimensions. So the first is called the coboundary expansion of the complex, which I'll define in a minute. And the second one, which is also important and much older, is called the spectral gap of the complex. And it will be of marginal interest to us in this talk, but it's very important in many applications. So let me say just a few words about the history of cohomological expansion or coboundary expansion. It first came up independently in work by Nati Lineal and with me and Natan Wallach concerning the homology of random simplicial complexes, and in Gromov's celebrated work on the topological overlap property. And it turned out later to have other connections, notably, for example, Alex and Tali Kaufman noticed that it has a very close connection to what's called property testing in theoretical computer science. As I said, the spectral expansion is much older, and it's essentially due to Ekman in the 40s, but the first real notable application is due to Garland when he computed the cohomology or the vanishing of cohomology of discrete groups. And then it had, I'm just pointing out two combinatorial applications, one to hypergraph matching, and more recently to the homology of Klee complexes by Matthew Cale. But we'll be mostly interested in cohomological expansion, so let me just define this cohomological expansion. It will be defined in terms of simplicial cohomology, so let me just recall the notation. We'll have a simplicial complex on V, some finite vertex set, and if we have a simplex V0 to Vk, we denote by sigma I, just the simplex with the vertex I deleted. The Ck will be the skew-symmetric maps on the K simplices. And the coboundary operator is just the usual dual of the boundary operator. So dk of phi on a K simplex sigma is the sum, alternating sum of phi on the faces of sigma. Okay, and Zk will be the kernel of dk. Bk will be the image of dk minus 1. These are the coboundaries. And the reduced K cohomology is just, as usual, Zk over Bk. Okay. Now, broadly speaking, expansion or cohomological expansion measures the following thing. First of all, we'll be interested in spaces X that have zero kth cohomology. So they are usually they'll even be K connected. And we want to measure to what extent they are really zero. So actually someone Israeli told me that If hkx is fs, then you want to see if it's fs meupas. So it's 0, it's 0 of 0, very 0. Okay. So how do we measure this, the extent to which this is 0? We measure the extent to which we have to change x in order to make hk non-zero, or the distance of x from complexes which have non-zero k cohomology. Okay. And for this, we actually generalize the notion of a Chigger constant as follows. Suppose that we have a k cochain, a phi in ckx. You can think of R as Z2, usually Z2 will be sufficient. We look at the support of dk phi. These are all the k plus 1 simplices on which dk phi is non-zero. So, okay. And now we call the Hamming norm of dk phi, and this is the main difference between the spectral definition and the non-spectral definition, that here we take really the counting norm. We count the number of simplices on which dk phi is non-zero, and this is called a dk phi norm. For example, if I'm looking at this one cochain, so I'm drawing the values on the edges, and we have, say, these three simplices, these three triangles, then on this triangle, if we work over Z2, d1 of phi is 0, because 1 plus 1 is 0, mod 2. On the other hand, on these two simplices, d1 of phi is just 1, so it's non-zero, and therefore d1 of phi is norm is 2. Okay, so we have the numerator of the definition. Now we have to normalize. So obviously, if this is big, then this means that dk phi is not a cocycle, and the larger it is, then the further it is from a cocycle. But we have to normalize, because if phi is big, then it will tend to have large dk phi. So how do we normalize? And this is called the cosystolic norm of a k cochain phi. So the natural thing would be just to normalize by the size of phi, but actually we have to be a little more careful. Namely, we prefer, or we should look at not the support of phi itself, but the minimum of the support of phi perturbed by a k co-boundary. So we take phi plus dk minus 1 of psi, where psi is in ck minus 1, and we take the minimum of this. For example, let's look at phi which is equal to 3. This is this phi. So its support is 3, but actually we can perturb it by adding to it the following co-boundary. This is a co-boundary. Adding to it the following co-boundary, mod 2, we get this plus this equals to this, and the support of this is just 1. Okay? This is the exact analog of taking, in the definition of the Chigger constant, the graphical Chigger constant, the minimum between S and S complement, or taking the smaller between S and S complement. So here we take, rather than norm of phi, the cosystolic norm of phi. Okay, and now we come to the main definition. If we have a cochain in ck, which is not a co-boundary, we define the expansion of this cochain as dk phi Hamming norm, normalized by a cosystolic norm of phi. And this is and this is and minimizing over all such phis gives us the expansion of the space. So some remarks: if G is a graph, then H0 really recovers just the Chigger constant, and the homology, kth homology or cohomology of X is 0 if and only if this Chigger constant is is positive. And we'll usually use just F2, although most things work for all rings, actually. So this is, as I said, is a measure of the extent to which H upper kx is trivial. And in many cases, we know about spaces that their kth homology is 0, but we want to quantify this, and this turns out to be quite useful. Now let's look at the first most trivial, so to speak, example, namely the expansion of the simplex, the n-1 simplex. So the n-1 simplex is, of course, contractible. It has no homology, and it should have, by justice, it should have very large expansion, and indeed this is the case. Hk minus 1 of delta n minus 1 is at least n over k plus 1. This is the analog of the statement that if you take a complete graph, then this is the ultimate expanders. Of course, it has other drawbacks, but it is, as an expander, it's very good. And so we have here this same conclusion, and we can see that in general it is tight. So if we take k to be equal to 1 here, so n is 2, we take this example, we divide the vertex set into three parts, equal parts, and we take the one cochain to be 1 on all these edges. Then the triangles that are hit an odd number of times, and actually exactly one time, are all the colorful triangles, these triangles. Their number is n over 3 cubed, and the size of this cochain, and actually its cosystolic norm is n over 3 squared, and the quotient will be n over 3. So this is the expansion of the simplex, but in general it's quite difficult to compute expansion, and this actually will be one of our missions to show expansion, or to approximate expansion of some complexes. Okay, let's say a few words about the origin of these notions. The first one is the concern random complexes. So let's think about random graphs first. Random graphs are just, you have endpoints, and the Erdős-Renyi model, you just pick each edge with probability p, and you can ask what are the properties of the resulting probability space. Here you do something similar. You take yk and p to be the probability space of all complexes which are k-dimensional, contain all the full k minus 1 skeleton, and now you add each k simplex with equal probability p, and independently. So let's think about the evolution of this space. So when p is equal to 0, then we don't have any k simplices. So it has huge k minus 1 homology. And as we are dropping into the complex, we are dropping k simplices, we start to kill, so to speak, k minus 1 homology, until, obviously, when we have all the k skeleton, then there is no k minus 1 homology. And the first question, natural question, which we studied with Nati and later with Natan Wallach, is where is this exact threshold where, when we start from k minus 1 skeleton and move up to the k skeleton, when do we lose all k minus 1 homology? And it turns out that the sharp threshold for this is exactly when p is k log n over n, which is an extension of the graphical case log n over n, and this is sharp. When p is slightly below kn over n, then hk will not be 0, and when p is slightly above, then hk minus 1 will be 0 with probability 1. But R here has to be a finite group, and the question for an infinite group like Z has recently been resolved, at least for k equals 2, by Yuval Peled and Luchak, student of NAPI. Okay, what is the relevance of expansion? The relevance of expansion to this question is very, very simple. Because let's look again at the bottom line. So we have many cochains, many k-1 cochains. And if you are looking only at the k-1 skeleton, all of them are co-cycles. Now, they are potentially also co-cycles of the space Y, of the random space Y. When they will not be a co-cycle, exactly when the cut defined by dk phi will not appear in Y. And the probability of this happening is exactly 1 minus p to the dk phi norm, which is by the estimate for the expansion of the simplex is at most 1 minus p to the cosystolic norm of phi times n over k plus 1. Now, and so you can think that summing over all phis will give you the result, and this is almost correct because what you get is the right order for magnitude, rather so something like k squared or k cubed times log n over n. To get the exact k log n over n, you have to do something else, but this was the original motivation. Okay, so this is the story with random complexes, but then we'll talk about the Gromov theorem, and for the Gromov theorem we need a slightly modify the definition of expansion, namely normalized expansion. So we look at all k simplices and we weight them according to the number of top simplices they are contained in. So the more top simplices they are in, the higher weight we give them, and we normalize so as to get a probability distribution. And again, we define the norm to be the sum of the norms of the simplices in the support of phi, and the cosystolic weighted norm to be the minimum of the cosystolic weights of phi plus dk minus 1 of psi. And the expansion is defined as before. So this is the normalized expansion, which is more suitable for different purposes. And now to the geometrical motivation for the definition of this expansion. And this is actually a beautiful story. Suppose that we have n points in space, in Rd, in Rk, and now we form k minus 1 simplices, and we want a point that will lie in many such simplices. So gamma a of p will be the number of k plus 1 subsets in n, such that p belongs to the convex hull of the AI. So we are talking about k simplices that contain p. Now, a remarkable theorem of Barney from 84 asserts that there is a positive fraction of all n choose k plus 1 simplices that contain a common point. Like you can see here some simplices with different colors that contain this red point. Okay? Barney's theorem is really a cornerstone in convex geometry, and it has many very nice applications also to computational geometry. And quite recently, and namely less than 10 years ago, Gromov obtained an amazing extension of Barney's theorem to the continuous realm. So rather than just a linear map of simplices, Gromov considers continuous map from the n-1 simplex into Rk. And again, gamma of p will be the number of k simplices, such that their image contains P. And Gromov's theorem asserts that there is a fraction of all n choose k plus 1 simplices whose image contain a point. So here you can see these no longer rectilinear simplices, but rather some kind of wiggly simplices, all of them containing this point. And you can see that not only he obtains a strengthening in terms of the assumption, he also gets a better constant. The best constant is not known, by the way, for k at least 3. Okay, so what is the connection with expansion? So now let's have, rather than the simplex, let's have just an arbitrary simplicial complex. We can assume that it's k-dimensional. And for a point P, let's count the number of simplices, k-simplices, whose image contains f of sigma. And assume that X is expanding in the sense that not only it is k minus 1 connected topologically, but hi of X are all uniformly at least epsilon, where epsilon is some constant, positive constant. Then Gromov says that there exists a delta, so there exists some fraction which depends both on k and on epsilon, such that for any continuous function from x to rk, there exists a point which lies in the image of at least a fraction of the simplices. So this is Gromov's theorem, and of course it implies his theorem for delta n minus 1 using the expansion of the simplex and the extension of Barney's theorem. Okay, so this is the motivation from convex geometry, or rather combinatorial geometry. And now the question is, can we compute, or can we come up with complexes that are expanding under different conditions? So, for example, as in the case of graphs, one would want complexes that are both expanding and they have small degrees in some sense, either vertex degrees or edge degrees, or depending on how ambitious you are. So now let me first talk about some method of finding the expansion of very common complexes like Metroids and buildings, compact buildings, spherical buildings. And this method is due to Alex and myself and Shachar Moses, and is motivated by work of Gromov, and we work on some complexes that are called building-like complexes. Let me not go into the exact details of what a building-like complex is, except for saying that it looks like a building topologically. So if we look at the apartments of a building, of a real building, so a real mathematical building, I mean, then these are imitated in building-like complexes. And the bottom line is, if we have enough symmetry in such complexes, then we get some lower bound on the expansion of X. And rather than decipher what's written here, I'll give you just two examples for very common complexes. One complex is matroids. So what is a matroid? A matroid is, well, here is a sort of fancy definition. A matroid is an n-dimensional simplicial complex on a vertex set V, such that if we take the restriction of this complex on any subset, then it will be pure. So all its maximal simplices will have the same dimension. Now, unless you know matroids, the best way to think of a matroid is by example. And a matroid can be obtained as follows. Take just a subset of a vector space. It could be an infinite vector space or a finite vector space. It doesn't matter. And take all the subsets of linearly independent that are linearly independent in A. So if you take all these subsets, then they are of course closed under restrictions. So if A is independent and B is contained in A, so B is also independent. So this gives a simplicial complex, and this simplicial complex is called a Metroid. Okay? Now, a nice feature of Metroids is that they are dim m-1 connected. So they have, in particular, they only have homology in top dimension. So it makes sense to ask, well, if they are dim m-1 connected, perhaps they are also expanding. So this is the question. And in order to be able to apply the machinery of building-like complexes, we assume that the Metroid will be symmetric, so its automorphism group will be transitive on the maximal faces. Okay? Some examples. One very simple example is you just take n+1 sets, V1, V2 to V n+1, all of size m. This will be n. Then and you take all colorful subsets, then these form a Metroid, and it's clearly symmetric. So this is one example. Another example is if you take a finite vector space and you take all linearly independent subset of it, then it also will be trivially symmetric. But there are also interesting examples like this. Suppose you take, this is particularly interesting because it's very non-intuitive. If you take a Hermitian unital with 65 points, so this is the set, and you take the independence matroid of this will also be symmetric. Okay. Now for these symmetric matroids, we have the following uniform bound. So if M is symmetric, then the expansion of M is at least some small number, so a to the minus dim M, but this small number only depends on the dimension. And the exact dependence is actually interesting, and we are not sure whether it's exponential or not. In many examples, we can actually improve this. So, for example, for the partition matroid, we have that the expansion of the octahedral n sphere is at least 1, which is the best. Actually, it's exactly 1. For partition, for the top dimension of a partition matroid, we have this number, which we don't know that is exact. It's probably not. And well, so this is the matroid, the story as far as we can analyze it. Another very natural example is spherical buildings. So let's look at the spherical building associated to SLN FQ, or SLN plus 2 FQ. We take all n plus 2, we take all subspaces of FQ n plus 2, and the simplices are, these are the vertices, and the simplices are just chains or flags. And a well-known theorem of Solomon and Titz says that the homology of this complex, of this building, is again trivial up to the top dimension, and this is actually the homology. And the question is, in view of this result, what can you say about the expansion of this building? And the answer is that actually it is expanding. And the result is that, and this is due to Gromov initially, it says that Hn-1 is at least 1 over n plus 2 factorial. And it's not clear how sharp this is because, for example, in the case, the two-dimensional case, we have a well-known exact result that the expansion is exactly 1, at least when q goes to infinity. Okay. Now, in the remaining time, I'd like to, okay, let me jump. I'd like to talk about some construction, probabilistic construction of expanding complexes. Now, but let's go back to graphs. And an expander graph is d epsilon, is a family of graphs which have these two seemingly contradiction properties. One is that it has high connectivity in the sense that the Chigger constant is bounded away from 0. And on the other hand, it's sparse. So its degree is uniformly bounded by d. Of course, it's a little bit redundant to tell this to the audience here, but the existence of regular expanders was first proved probabilistically by Pinsker in the 60s. Then Margulis gave an explicit construction, and then the LPS, the famous Lobotsky, Phillips, and Sarnak, and Margulis gave this sort of optimal expanders. These are the famous Ramanujan graphs. Now, one can ask, what happens in higher dimensions? So we'll be least ambitious and define the degree of a simplex to be, of a k-1 simplex to be the number of k simplices that contain it, and we'll define a k d epsilon expander to be a family of complexes with number of vertices going to infinity, such that the degree of any k-1 simplex is bounded by d, and the k-1 expansion is at least epsilon. Note that we can be more ambitious and ask for the degree not of k-1 simplex, but of say a vertex to be bounded. This is harder to do, and actually I'll say a few words about it at the end of the talk. But we'll be content with saying something about this. Now, the question is, do there exist k d epsilon expanders with k at least 2 and fixed d and epsilon? And the answer is at this point that this is known for any d and epsilon. And I'd like to say a few words about joint work with Alex on d equals to 2. So we'll be concerned with d equals to 2. So we have a complex whose two simplices will have two simplices such that any edge belongs to at most d two simplices, and it will be an expander. And we construct it probabilistically in the following way. So it will be constructed from Latin squares. So what are Latin squares? These are Latin squares, of course. There is a definition here, but of course a Latin square is just a square, an n by n square with 1 to n in each row and column, and okay, this is a Latin square. But it may be easier to think, or more suitable to think of a Latin square as follows. It will be, okay, so let's look at this complete three-partite complex. So this complex consists of all edges and all colorful triangles. So a triangle will be inside if it's colorful. Then a Latin square is a subcomplex of this complex, such that any edge belongs to exactly one triangle. This is trivially a translation of being a Latin square. So altogether we have n square edges here, n square edges here, and n square edges here. So 3 n squared edges, and the number of two simplices is exactly n squared, right? Because for each edge here, it can be completed uniquely to a 2 simplex. Now, topologically, a Latin square is very boring. Why? Because here I'm drawing the Latin square, which corresponds to the complex that corresponds to the Latin square 1, 2, 2, 1. So the 1 tells us what are the neighbors of A1. So the neighbors of A1 are B1 and C1, and B2 and C2. These are just the indices of this place and this place. On the other hand, the 2 here tells us, or the color 2 tells us the neighbors of A2. So the neighbors of A2 are 1, 2, so it's B1, C2, and C1 and B2. Okay, but topologically this is boring because it's only seemingly two-dimensional, because you can collapse all two-dimensional faces here, because all the edges are free. So all the edges, you can push them inside, and you can essentially get rid of the two simplices. But this is when you take one Latin square. If you take another Latin square, this is already getting to be interesting. So if you take, if you take a union of this Latin square plus this Latin square, then already you get the full octahedral two-sphere, and this already has interesting topology, mildly interesting. It's S2. So the idea is to take a union of many such guys and get a complex which on one hand will kill all one homology, and furthermore will have positive one expansion, and on the other hand will have a bounded edge degree. Okay? And we do this by simply taking D-independent Latin squares, just independently in the space of all Latin squares. So this is the probability space, Ln to the D, and take the union of the complexes that they generate. And the claim is a probabilistic claim. It says that with probability approaching 1 as n goes to infinity, this complex will have h1 of y at least epsilon. Here, d and epsilon are fixed. So I just hid them a little bit because they are a little embarrassing. They are epsilon that we get is 10 to the minus 11, and d is 10 to the 11. But in any case, they are both finite and both luckily slightly positive. So it's at least nominally it's okay. Now, the ingredient of the proof there are two ingredients, and actually I'd like to say a few words about Alex. So we usually met in his office to work, and but one time he had to babysit for his baby granddaughter, I think the daughter of Boaz. So we met in Boaz's place, and then I noticed that Alex is very capable of doing two things at the same time, namely doing mathematics and changing diapers, very expertly. So, yeah, there are several breakthroughs. Yes, indeed. So it was exactly the time that you changed diapers. Okay, so there are two ingredients. One we consider small cochains, and big cochains. So small cochains will be when its cosystolic size norm is at most Cn squared, and when it's big, when it's at least Cn squared, it's big, C large. For small cochains, we use a lower bound on expansion on the one expansion in terms of the spectral gap of the vertex links. So the vertex links in this case are just graphs, and you can analyze these graphs, and they are random graphs, and use some result of Friedman about random deregular bipartite graphs, and you get what you want from from this. The C large cochains have to be treated by somehow understanding the space of Latin squares. The space of Latin squares is not something that you can work off very easily because you cannot count them readily. You can just somehow estimate their size. And so this is another ingredient. So let me just say some words about the first ingredient. So suppose that we have a subcomplex that contains the full one skeleton, as we had in the picture, and contains some simplices. And we look at the links of vertices, and we look at the spectral gap of each link. The spectral gap of each link is a bipartite graph. We look at the spectral gap, and suppose that all these spectral gaps are positive, and let lambda tilde be their minimum, and let D be the maximal degree of an edge in Y, then the expansion of D1 of phi is at least this quantity, which is a constant, some constant, times the cosystolic norm of phi, which guarantees that if this number is bigger than 0, then we have expansion. D1 of phi norm over the cosystolic norm is positive. And then using some estimates for if C is small enough and the vertex link are good enough expanders, then we get that this is positive. So this would be around D. So we'll have D over 2 minus D over 3, which is positive, and then we are okay. So this is one ingredient. The probabilistic ingredient concerns large deviations in the space of Latin squares. But let me first say one word about permutations. Suppose that you have just a set of tuples, or as combinatorials will have it, it's just a bipartite graph on n by n vertices, which is dense. It has at least Cn squared edges. And for any permutation, we look at the number of I, such that I and pi I is a member of E. Then obviously the expected value of this random variable is E over n, because the probability of an edge appearing is 1 over n. So it will be C over n. And now one can ask, what is how concentrated is this random variable? And it turns out, and this is a result of Murray, that it is very concentrated. So the probability that G will be less than the expected over 10 is exponential in n. And the exponent is minus C squared n over 20. Now, Murray's theorem is actually a part of his theory of obtaining large deviations using martingale. But actually, there is another approach. And this approach gives a slightly better estimate, namely dependent not on C squared but on C, which is better when n is when n is big. Yeah. Okay, and this approach turns out to be, we can push it to the Latin square case, and in the Latin square case, suppose here now that we have a subset of simplices whose cardinality is Cn cubed, and we look for at a Latin square will have n squared two simplices. We look at these two simplices that actually hit E. The expected number of such simplices is Cn squared, at least Cn squared. And the theorem is, again, a large deviation theorem. It says that this probability that a Latin square will hit E in less than, say, 10 to the minus 3 C squared n squared is this time at most E to the minus n squared times some constant. And this turns out to be the key to the second part of the proof. Okay. Now let me just finish by some comments and conjectures. So one natural conjecture for this model is that D doesn't have to be 10 to the 11 or even 100, but we can. It's valid. The theorem is valid for D equals to 4. So 4 Latin square are already random Latin square are already expanding. Another comment is what happens in high dimensions. So in high dimensions, this method was extended by Alex and Tsur Luria and Ron Rosenthal. Actually, their proof uses random Steiner system and depend on Kiva's groundbreaking work on the existence, on the distribution of such Steiner systems. And then for the more for the harder questions of bounded vertex degree, where here again it's work of Alex and Tali Kaufman and David Kashdan, and for D equals to 2, and Shai Evra and Tali Kaufman for general D, that they prove that the D skeleton of a D plus 1 Ramanujan complex, which probably Shai will tell us about, such a complex is a topological expander. Now, a topological expander is something which is weaker than a cohomological expander, but it gets close. And I think they conjecture that most Ramanujan complexes are also coboundary expanders. Happy day.